Welcome back. We're in chapter 4. We're looking at Newton's laws of motion, and I want to look at this example 415 from the textbook. Now, in the textbook problem, if you're following along, it actually calculates. There's part of it I left out where the car is accelerating forward and the ball. Well, let me take a step back here. The situation is we have a ball suspended from a string by a string from the roof of a vehicle. And as the vehicle sits still, the ball just sits straight down. If we were to draw a free body diagram, the only forces on this ball would be gravity pulling it down and tension in the rope pulling it up. And that's it. Now, as the car accelerates, if the car were to accelerate forward, the acceleration would cause the ball to swing backwards. So the ball would come over here. And then there's a part of the question in the book is, what is this angle if the car is accelerating at a certain rate? And honestly, the algebra just gets a little too complicated, I feel, for the purposes of this class. So rather than looking at the calculation of what the angle is, I want to focus on something that is conceptual here. So the thing that I want to focus on is the part of the question that asks, what angle does the string make when the car moves at a constant velocity of 90 kilometers per hour? Okay, and the common misconception that people have is that if the car is traveling down the road at 90 kilometers per hour, the ball is going to swing back and be at some angle here. But constant velocity means zero acceleration. Because if we think of the definition of acceleration, acceleration is equal to the change in velocity over the change in time. If velocity isn't changing, then that's equal to 0 over delta t. So it doesn't matter what the delta t is, it's always going to be equal to 0. And if acceleration is equal to 0 and force equals mass times acceleration, then the force would be equal to mass times 0, which is 0. So if there is no force, if the force acting on the ball is 0, then it's not going to swing back at all. It's going to, the string is going to be perfectly vertical, and the only two forces acting on it are going to be gravity and the tension in the string. And that's it. So constant velocity implies 0 acceleration. And in the absence of acceleration, there is no force. So the mass does not move. So it's when the car is accelerating, when the car is changing its speed, when you hit the gas pedal and the car begins to accelerate, the ball has inertia and wants to stay put. The rest of the car accelerates forward, and so that causes an acceleration on the ball, and the acceleration then causes a force, and that force causes the ball to swing backwards. Okay. In a previous problem, we looked at a box sliding along a tabletop, and we made the assumption that that surface is frictionless, because friction does complicate calculations a bit. But friction is something that is an inescapable part of our world. It's caused, if we look at this microscopic level, these two seemingly flat, smooth surfaces. Any smooth surface, if you look closely enough, is not perfectly smooth. Some surfaces are smoother than others, but there are some high spots and low spots on both the box and the table. And these irregular surfaces interlock with each other to varying degrees, and that causes what we know as friction. Friction always opposes motion, and there are two types of friction. There is static friction, and there is kinetic friction. So if we look at kinetic friction, the force of friction is equal to mu sub k times Fn. Now this we have talked about before. F sub n is the normal force. So if you think back to that slide we have with the statue of Abraham Lincoln sitting on a table, whatever its weight is pushing down on the surface pushes back with an equal and opposite force, and we call that force the normal force. So the normal force, which is perpendicular to the surface, multiplied by this coefficient here. Now this is new, we haven't seen this yet. Mu sub k is the coefficient of kinetic friction. So the k is for kinetic, and the other type of friction is static friction. So basically, if the box is sitting still, you have to apply enough force to overcome the static friction force in order to get it to start moving. We could call that the pulling force. But once we get it moving, it's easier to keep it going. And that is because the kinetic coefficient, or the coefficient of kinetic friction, is less than the coefficient of static friction. This table, 4.2, comes from the textbook, and it shows coefficients of static and kinetic friction for a variety of surfaces. These are basically just average values. They're approximate values. They can vary depending on a number of different factors. But you can see that in some situations where we want there to be a good deal of friction, like tires on a road, rubber on dry concrete, we want there to be a pretty good amount of friction there, and so that's 0.8. That's relatively high. That's what's going to keep your car from sliding off of the road. When it is wet, when it rains and the road gets wet, you can see that coefficient of kinetic friction becomes less. It drops from 0.8 to 0.5. So we can see clearly that roads get more slippery when they are wet. And then things where we want to reduce friction, like a lubricated ball bearing. We want to avoid friction and make them move as easily as possible. That's 0.01. That less than 0.01. That's pretty low. And even in human biology, things like the joints, your knees or elbows, those joints have a very low coefficient of friction as well. So the coefficient of static friction can be used to find the friction force that needs to be overcome initially to get something to start moving. So if something is sitting still and you want to push or pull on it and make it move, you need to apply a force that is greater than the friction force, which is going to be equal to the coefficient of static friction multiplied by the normal force. Once it starts sliding, it will be easier to keep it going. The coefficient of kinetic friction, let's look back here at this chart. Kinetic friction is less than static friction. So we looked at rubber on dry concrete. The kinetic friction is 0.8. The static friction coefficient is 1.0. So you can see it gets a little bit less. And that's the case with all of these materials. We're going on wet concrete from 0.7 down to 0.5. So what this tells us is that it takes a little bit more force to start the object moving, but once it is moving, it's it's a bit easier to keep it going. Let's look at an example problem here. This is very similar to the problem we looked at earlier, only this time we are going to consider friction, and the pulling force that we are applying is not horizontal. We're applying it at a 30-degree angle. So the mass of the box is 10 kilograms. Let's write that down, 10.0 kilograms. And the FP that we're applying is 40.0 newtons. And it's applied at a 30-degree angle. And the coefficient of kinetic friction is 0.30. So we're going to assume that we've got the box moving and we want to keep it moving. And we want to know how it is going to accelerate, what the acceleration is going to be. So earlier, when we didn't consider friction, we just said, okay, these two forces cancel each other out, so we don't have to worry about them. Well, in this case, we do need to worry about them because we need to know what the normal force is, because the normal force is going to affect what the friction force is. So I'm going to advance a slide here. So we need to find out what this normal force is. Now, if we weren't pulling up at an angle here, we would simply say the normal force is equal to the weight. The two are going to cancel each other out. That's not the case here, because when we're pulling on this box, we're not only pulling it to the right to make it slide, but we're also pulling it up. By lifting it up, we are reducing the normal force on the box. So if we sum the forces in the y direction, in the vertical direction, the forces that are present are mg, that's in the downward direction, plus Fn, the normal force going up, plus the vertical component of this force, which is Fp sine of 30. We use sine of 30, sine of the angle, to find the vertical component of a vector. Now, we can assume that the force that we're applying here, this diagonal force, is not so great that we're going to actually lift the box up off of the ground. So we can assume that there is no vertical acceleration. And so if there's no, so it's mass times acceleration. So we can assume that the acceleration in the vertical direction is 0. So what we're saying is these three forces are going to cancel each other out and all equal 0. So the mass of the box was 10.0 kilograms. Gravity is 9.80 meters per second squared, acceleration due to gravity, plus the normal force, which we don't know, plus the pulling force, which was 40.0. Was that newtons? Was that given to us in newtons? Yes, it was. 40 newtons times sine of 30, and that all is going to equal 0. So if we solve for Fn, Fn is going to equal 10.0. I'm going to drop the units out for now just to clarify the algebra. 10.0 times 9.80. So I've added this term to the other side, so it becomes positive. I'll now subtract this term, minus 40.0 sine of 30. Okay, and so the normal force should work out to 78.0 newtons. So that's what the normal force is. Looks like I'm coming up on my 15-minute limit, so I'll stop right there and resume this example problem in the next video.